All right, welcome back. We're going to learn now is charge controller and inverter selection. These are the electronics that process the electricity from the solar panels, put them into our solar array, or put them into our electric load. And when you go off grid, you might have a question of, well, are off-grid components any different than grid-connected components? And the answer is yes. Local jurisdictions have their own rules and regulations, and maybe not all of them are well thought through. In particular, the disconnect requirements of grid-tied systems have been kind of passed down from one program to another, and you go circle back to the original program and they say, well, actually we kind of overdid it with our disconnect requirements. In fact, in particular with the AC external disconnect for solar arrays, that's a common jurisdictional requirement. You won't find it in National Electric Code, at least the kind of knife switch requirements that many jurisdictions require. And the reason is that these external knife switch disconnects that are readily accessible, they can actually represent a safety hazard to the design, in the sense that you have a readily accessible, anyone can walk right up to a disconnect switch, and all it takes is a screwdriver to remove the front plate of that disconnect switch. So if your customer, 5 years down the line, wants to kind of explore the insides of their solar array, you now have a readily accessible access point that just by someone taking a plate off with a screwdriver and sticking their hand inside, they could quite easily electrocute themselves. And for that matter, the listings of these inverters for things like automatic shutdown when the grid failures, they used to not be around. But now they've been around for over a decade. And so the call for these lockable, taggable, obvious third-party disconnect switches that go above and beyond the disconnect switches on your service panel. So your service panel has a disconnect switch that, in the eyes of National Electric Code, is a main disconnect switch, except for perhaps the reason that it goes left to right rather than up and down. A minor point compared to safety. But the point is, a grid-connected inverter goes through a lot more review than an off-grid inverter. In an off-grid inverter, you might have all the disconnect switches being built into the inverter itself, and then the local jurisdiction comes along and says, oh, you need an external disconnect switch. And that might kind of defeat the point of all the internal switching that goes inside the internals of the inverter, particularly with regard to, say, a automatic transfer switch. You might have an automatic transfer switch within the inverter itself, but your local jurisdiction says, well, we want an external automatic transfer switch, one that we can really open up and see inside so that we know definitely that it's going to work. And so you can't use that automatic switching functionality of the inverter. Well, for that matter, your grid-connected inverters, they go through product iterations, and if you discontinue a certain product line and roll out a new product line, you now have to go through UL certification, which is an expensive process. And so you have testing fees associated with that. Furthermore, UL certifications is a fluid process, so they may come out with a new listing that then the inverter has to get relisted for. And many of those listings have to do with grid connection. So an off-grid inverter may perform just as well as a grid-connected inverter. but it has not incurred the cost of going through a listing for grid connection. It may have a transfer switch that is perfectly suitable for switching between battery power and generator power, but that transfer switch is not suitable for an interconnection with the grid. And so, in fact, there are a class of off-grid inverters which have very similar functionality and performance to a grid-connected inverter, yet they are substantially cheaper, to the tune of, comparing a $1,200 inverter to a $3,500 inverter. And so if we are counting our pennies and nickels and dimes, you might say, well, wouldn't I rather spend that $2,000 difference on my battery capacity? Because batteries are expensive and we're going to have to overcome that cost hurdle to go off grid. Why would I need the additional cost of a grid connected inverter? On my very first off-grid system, I went with a grid connected inverter. And the reason was I had never done an off-grid system before. If I messed up on my design, I would humbly tell the client that no, they needed to build the electric grid out to their property and hook the system up because I made a mistake with my design assumptions and something went horribly wrong, and in fact they needed that grid connection. Now luckily we did not have to do that. The most expensive battery inverters are listed for grid connection, and they are feature rich. They have tons of features. Now, why don't I just pull up the internet for a minute and do a kind of a real-time example? Oh, I guess I already have it in this example. Maybe not. Yeah, so let me just pull up the internet for a minute. So what we're going to do is we're going to go look at an Ames inverter that is not listed for grid connection. And this is not a top-of-the-line efficiency inverter. It is not the top quality inverter. Now, we've learned by now that efficiency really is not the end-all in off-grid. And so we see they have some products that are certified to UL listing and some products that are not. So let's go and look at the 48-volt pure sine wave inverter. We'll check out their product line. Generally, I'm going to go and look at the top of the product line, and here we have a 12 kilowatt pure sine wave 48 volt inverter with 120 to 240 volt split phase output, and it's not UL listed, it's ETL listed. Some jurisdictions will accept the ETL listing just as well as the UL. Other jurisdictions, they've been told they need to look for UL 1741, and they will not accept anything but UL 1741. But that's a grid listing, a grid-tied listing. If you're going to stay off grid, you do not need the UL 1741 listing. And so here's this Ames 120, 240 volt inverter. And we'll talk about some of the features going on. We see how it has terminals for landing the batteries. It has some AC input and AC output, an auxiliary output for a pump. Really what I want to focus on right here is the price. It's $3,099, and remember this is for a 12 kilowatt battery inverter. And then from that point you're going to have to go and put a charge controller on it as well to go between the solar array and the inverter. So it's not the only point that we need. So I guess what I've done in this cost example on the slide here is said, okay, we're going to buy the $3,000 inverter, and then we're also going to put 2 big charge controllers. And so our total inverter system, the 2 charge controllers that are large, plus the Ames inverter, is going to be a $5,000 system that's going to give us 12 kilowatts of inverter capacity. And while it has all the landing terminals and switches to wire everything up, it probably isn't going to meet the local jurisdiction requirements that'll say, well, we want that UL listing. We need you to put it on additional disconnect switches. Alternately, we can go look at a grid-tied battery inverter, and I'm a fan of this battery inverter as well. This is the Schneider 120 volt, 240 volt split phase, so we're kind of doing an apples to apples comparison here. And what we see is that this Schneider inverter costs more than the 12 kilowatt Ames inverter we just looked at. Well, why does it cost more? Well, one is it's rated for grid connection. The Ames inverter is not. The Schneider inverter has more support. They have tech support. And it's good tech support. I like having tech support. I like not having to figure out the answer to every question. But what we can see is, let's pull up the spec sheet. Kind of scroll down. And there we go, right here. We have the UL listing. It's incurred more cost. And actually, it's only 6.8 kW, so if we wanted the full 12 kilowatt output, we would actually need to get 2 of them. So 2 $3,500 inverters. That would bring the price, maybe with some competitive bidding, up to $6,000. Well, then you need a distribution panel to wire the 2 inverters together. And actually, this doesn't include the full cost, because then you would still need to go and buy the $2,000 charge controllers that we put into the previous example. So, to get a 12 kilowatt off-grid inverter, you'd be looking at $5,000 in cost. Or if you went with the grid-tied option, by the time you got all the pieces together, you could be looking at a $9,000 or $10,000 system compared to a $5,000 system. And so it might be that you go and you look for a one-stop shop that has all the wiring, all the transfer switches for your generator, everything you need put into one unit. And because that one unit is not listed for grid connection, it's cheaper. Then again, there's no such thing as a free lunch. By spending more money, you do get more features. Maybe not all these features are necessary. One feature that I think is very important for off-grid living is double redundancy. So this is an engineering term that says, if you have one component that fails, the system still operates, maybe at half capacity, but not at 0% capacity. So if you have one system component that fails, you don't lose your whole system. So a residential home is not usually doubly redundant. If your main breaker fails, you're out of power. If the utility transformer fails, you're out of power. A home with a backup generator is doubly redundant. Well, in off-grid, we have to think about if our inverter fails, now our customer's out of power. And so having two inverters, having two 6 kilowatt inverters instead of one 12 kilowatt inverter does offer an extent of double redundancy. Now, I don't like microinverters. Microinverters go behind every single panel, and what that means is you have a failure point behind every single panel. And so, you go for not double redundancy, but quadrillion redundancy, and you end up just doing a lot of maintenance work because you have a lot of failing parts. So we're not talking about inserting a whole bunch of failing parts into our system design. We're just saying, rather than having one inverter, it might be better to have two inverters. Keep it simple. If you have emergency power systems, you might go for triple redundancy as like a extreme maximum. Now, we also have the generator there in addition to the inverter, so it's not like we're completely without options. But again, running a generator 24/7 to get the problem fixed is very expensive. In our last model, we showed our generator had a runtime of 48 hours a year. And I even thought that was too much, and that we might increase the battery size later to reduce the generator runtime further. Running your house 2 days on a generator is going to be an expensive way to generate electricity. We don't really want to plan for that, although it is there. So, is it the end of the world if you don't have two inverters instead of one? No, you do have the generator there for backup. But then again, it is kind of nice to know. I mean, I made a mistake on my design. What happened was, these are 80 amp charge controllers, and the breakers are specialty breakers. And we realized as the stuff was being delivered to site that the breakers did not come with the charge controllers. And so, I quickly ordered two 80 amp breakers to go with the 80 amp charge controllers, and I made a mistake, which is I should have oversized the breakers. Because if these charge controllers were running at their full capacity, they would be outputting 80 amps. And so I thought, well, why don't we just wait and see what happens? We'll wait and see if the charge controllers ever get up to outputting their full capacity. Well, lo and behold, we got into a springtime day where the sun is shining directly on the modules. We were doing some construction equipment, and so the construction equipment is pulling, high startup loads. And the inverters were telling the charge controllers to take the power out of the array rather than out of the battery. And so the charge controllers were spiking up to their full rated capacity. It was also a hotter day, and that, hot days are going to decrease your voltage dramatically, but also uptick your amperage somewhat. And so all of a sudden, we have a breaker trip. One of the two 80 amp breakers tripped. Well, guess what? The other charge controller kept working. It had fewer modules on it than the overpowered one. And so that other charge controller and the other solar array kept working, and so the battery bank did not run out of electricity, even though there was something wrong with the system. And that allowed us to order the new breakers without it being an emergency, and that was kind of nice. That was a example of double redundant architecture working. Whereas if something inside this single inverter goes wrong and it causes the inverter to completely shut off, and it's kind of hard. Maybe that doesn't always happen. Maybe inside this shell, because all this is a shell maybe inside the shell there's two charge controllers, and so if one charge controller fails, the other charge controller might keep working, and so you might have a component fail inside a single inverter and not cause a system-wide failure. Still not as good as having two inverters. And double redundant architecture isn't perfect either. It turns out that when you have two inverters wired next to each other, you'll program one to be the controller and one to be the follower. And what happens is if the follower has a failure, no big deal. The controller just keeps going along its business. If the controller fails, the whole system shuts off, and then you have to go and press a couple of buttons to say, okay, what was the follower, now you're the controller, and then the system starts back up again. So it doesn't, even if you have a double redundant architecture, you may not have a function that automatically swaps the roles of the inverters so that you don't lose any system uptime. You still might have a maintenance event involved in getting the system back up and running, and maybe that's not such a bad thing. You know, if something goes wrong with your system, you want to know about it. You don't want to just leave it go unaddressed. What is particularly useful about a double redundant inverter architecture, they call these stackable inverters, where you can have one, well, you can add on another. If you need more power, you can add on another. So often in the off-grid realm, if you want to have three-phase power, you'll be ordering 3 inverters, one for each phase. You know, in that case, a doubly redundant architecture might mean you have to have 6 inverters, because 3 would be kind of your starting block. And so there's stackable inverters. Now this Ames inverter that's cheaper, it's not stackable, which means if you go and design a home with a 12 inverter kilowatt output capacity, and then for whatever reason, you know, maybe they get 2 electric vehicles and decide to put in a hot tub, well, they're now beyond the operating requirements of their inverter, and so they have to scrap it and go back and put in a new, more expensive inverter system. And I've 12 kilowatts for a single battery off-grid inverter within like residential product classes is about as large as I've found. I haven't, you know, what I would like to see is something like a 20 kilowatt battery inverter, maybe even a 50 kilowatt battery inverter, but I haven't seen any on the market yet. You know, if it was my home, and I was budget constrained, I would go with the cheaper system. I wouldn't go with the more expensive system, even though I like the Schneider system. You know, the Schneider system is for people who want to have their cake and eat it too. You know, they want to have the feeling of an off-grid system. Maybe they want to run their whole house off-grid, except when they absolutely have to, but they still want to maintain that grid connection. And that comes with more bells and whistles. It's also a more multifunctional inverter. It's an inverter that can be used for commercial demand management, as well as off-grid residential living, as well as a generator assist, which is kind of a weird mode where you probably for more island living, where you're running off a generator full time and the inverter is just there to kind of smooth out the spikes in load by load leveling for the generator. You know, there's a lot of different modes of operation. There's a zero export mode where it meters the grid, and whenever you're exporting to the grid of power, it stops the charge controllers, it stops the output. You know, a couple of different modes of operation, a number of UL listings, flexible platform where it can do 60 hertz or 50 hertz. You know, all of those additional features cost money. And so you get into the high-end range of your battery inverters, and you aren't necessarily going to use all of those features. So if you're budget constrained, going with a single battery inverter that, you know, solar installers maybe they've never heard of Ames as an inverter manufacturer because they've never considered doing just an off-grid inverter. And so when we're looking at cost differences between the off-grid only or the grid tie only inverter, we may be looking at cost differences of $2,000 to $4,000 in material cost. And then if our utility is charging us solar discriminatory rate structures and not giving us anything more than avoided cost electricity for our outflow, like we saw with Coast Electric in South Mississippi, we saw in that example we would have to spend $8,000 on additional solar capacity just to overcome the fees that the utility was putting on their solar owner to administer that grid-tied connection. And so you might be looking at anywhere between $10,000 to $12,000 of additional total cost to be grid connected while having a system rated for off-grid living. And when you're talking about that much money with industrial flooded lead acid batteries, we're talking about half the cost of the battery bank right there. And so depending on how, not just depending on the additional cost to remain grid connected, the smart meter one-time installation fee, any solar discriminatory fees, the differences between the net metered and the avoided cost compensation rates. But then if you say, well, okay, what if I just go completely off-grid and don't have the grid connection? You do get into a cheaper class of materials that isn't necessarily a worse class of materials. It's just inverters that don't have all the functions of a grid-tied inverter, and you might not need all those functions. So you're not paying for stuff that you don't need. And also another real benefit is no more interconnection applications. So if you're, this doesn't apply to all jurisdictions either, but if you're in a jurisdiction where they say, well, you have to give us the application 30 days before the project, and then you can't operate the array until you schedule an inspection with us, and we're not going to allow you to power up the system until inspection, so you're not going to know if there's anything wrong until we get out there, and if something goes wrong, you're going to fail inspection, and then you have to reschedule the inspection. And so getting through the interconnection application process might take 2 months, whereas the design, material order, and installation might take 2 weeks. So you avoid all that, and shortening a project development cycle from 3 months down to 1 month, that alone can mean you're doing more business. That alone can mean you can sell at perhaps a lower margin. And that alone can free up money, therefore, for the customer to put into that expensive battery bank. There are also minimum battery bank sizes that these battery inverters require to function. It's kind of interesting. The SolarEdge storage with the lithium ion, they actually say you don't need to do the battery yet. You can buy the battery inverter but not put the battery on it, and it just functions like a batteryless inverter. When you get a whole house, not a critical load panel, but a whole house backup battery inverter like Schneider, they say, no, you got to put in a battery. And the minimum size of that battery is 20 kilowatt hours about for a 48 volt battery bank. And so it's not like you can just go and plug in a $200 battery that doesn't do anything more than just turn the inverter on like a generator. They have a $100 battery that goes inside a whole house backup generator that acts as the electric start for a generator that doesn't have the crank start with your hand. You press a button, the generator turns on. There's a battery inside that generator. For these battery inverters, you read into the spec sheets for the Schneider, the minimum amperage is 440 amp hours. And so if you're doing a 48 volt configuration at 440 amp hours, that's a 20 kilowatt hour flooded lead acid battery. And then it's kind of hard to find an industrial flooded lead acid battery that just has 440 amp hours. Usually they start at around 600 amp hours or 800 amp hours. And so you're not buying a 20 kilowatt battery, you're buying a 30 kilowatt battery or a 40 kilowatt battery. And so there are kind of minimum buy-in costs for going with these heavy hitting battery inverters. Now, you don't have to do an industrial flooded lead acid battery in that case. You could go down and do a AGM sealed battery that and in that case, and you don't need to do a 48 volt. You could go and do a 24 volt. So, maybe you could configure it to be a 10 kilowatt hour battery and not spend so much. But in that case, what you're buying is basically a battery that's not going to do anything for you. It's just going to hang out and hardly ever operate. And then if there's a blip on the power grid, just like with the Tesla Powerwall, you might be able to have, a couple hours of power. Well, in this case, you'd actually have a couple hours of whole house power. Well, that's still not necessarily true. When we'll get into our one-line diagrams, what we'll see is these Schneider off-grid inverters, they still have outputs for your whole house plus outputs for the critical load panel. Because again, that output that goes to the grid is not going to disconnect during the power outage, and so they have to kill the power to that whole house. And so, if you go with a small battery that's just going to hang out and not do anything, you're still getting into the realm of like the SolarEdge backup inverter where you have a critical load panel. It's not a whole house system. If you want a whole house system, at that point, you would then need to go and get an automatic transfer switch, which costs $1,200, which then gets back into what additional hardware do you need to throw into the system to get your grid-tied off-grid system to completely disconnect from the grid and actually run your whole house during an outage and not just a critical load. And so when we're talking about $1,200 for a automatic transfer switch and $3,500 for the premium on the grid-tied battery inverter, right there we're saying the hardware cost, all else being equal, forget net metering, forget about the additional power. I've kind of lowballed this number for the slide. What this should actually be is not $2,000, but really about $4,000 of additional hardware costs in order to get a UL listed battery inverter for grid connection plus an automatic transfer switch, just the material, not even including the installation, to put out the front of your electric service so that you can take your whole house off grid automatically and power it during that power outage without having to do anything else. And so if it's me and I'm looking at a $20,000 battery bank to go completely off grid, or I'm looking at spending maybe $4,000 in batteries for batteries that are just going to hang out and kind of do nothing, and then $4,000 in additional costs to maintain that grid connection, I'm really looking at the difference between spending $8,000 and still having a system that's not going to ride me through the worst disaster possible, versus $20,000 and having a system where I'm never going to have to mess with the electric grid again and not pay those meter fees, etc. And so at that point, kind of what becomes the tipping point is how good of a deal the utility is willing to compensate you for your outflowed electricity. And if, like in much of the Southeast United States, if like in much of the rural electric cooperative areas, some states that have net metering will exempt the electric cooperatives from the net metering regulation. So this is a case-by-case basis, but if you're in one of those jurisdictions that just has terrible solar policy and you want to go off-grid, you might find that it's really just a difference of paying additional $10,000 in batteries and then the avoided cost of the hardware, chunk that into the battery bank, and then go get a cheaper battery inverter than what you had originally selected, and all of a sudden, you're off grid. Maybe you have to finance that additional cost and you didn't want to finance it, but you might want to look at is your finance fees greater than that monthly grid connection? Because if it's less than the monthly grid connection, then you have that might be something to consider. Another debate is whether you want to do DC coupling or AC coupling. I have to let's see here. Doesn't look like my display is set up correctly, so let me try and fix that real quick. Just hold on. So I'm recording this. There's some students who kind of want to get started on this content. Just refer to the course slides that are linked to in the Slack for the previous discussion until I edit this out in the video and replace it with the Alright, and the last thing. Well, let me just go switch screens here. There we go. Alright, that should do good enough. Kind of a opposite setup than what I had going on yesterday. Okay, so we're back. You may have a question of, should you do DC coupling versus AC coupling for off-grid? We've seen that AC coupling is a pretty good choice for grid-connected battery inverters. It's a little bit more efficient than DC coupling for grid-connected battery inverters. Although, in our intro to battery class, we do point out that the DC charge controllers, they are cheaper than their inverter counterparts. Now, right now it's a very close race because there's a lot more inverters being manufactured today than there are charge controllers. This batteryless solar market has really ramped up. And so we get a lot of cheap inverters on the market today. And so right now the price difference between an inverter that you would AC couple next to a battery inverter versus a charge controller that you would put ahead of the solar array and battery bank before you go onto your battery inverter, That's really the question when you say, do you do DC versus AC coupling? What you're actually asking is, do I tie the solar array onto its own inverter before I get to the battery bank? You're buying the battery inverter either way. You're buying the batteries either way. The real difference is, do I buy an inverter for the solar array before I land on the batteries, or do I buy a charge controller and just directly tie the solar array into the batteries? And if you're grid connected, AC coupling is generally the way to go. It's a very easy retrofit where you probably already have the solar array and the inverters. So you probably already have the solar array and the inverters installed. And so then when you retrofit, you just go and add a battery inverter and a battery bank, and you still have that grid connection. And so that's easy. It's easy to AC couple. And the cost difference, technically the charge controller should be cheaper than the inverter because it's just doing a DC to DC voltage regulation. It's not doing a full-blown DC to AC voltage regulation. And technically, the charge controller should be more efficient because in this case, we're going from our solar voltage, stepping it down to grid voltage, and then reprocessing it through our battery bank, and then reprocessing out of our battery bank. But in reality, we have had so much research and development and economies of scale go into these batteryless inverters that they're about the same price as the charge controllers. So much research and development has gone into these batteryless inverters that they're about the same efficiency as the charge controllers. And then most of the power from your grid-tied solar array is not going to go into your battery bank, but instead is either going to go into your load or the grid itself. And so, for the ease, and what it becomes is it doesn't really matter if you do DC or AC when you're grid-tied. But when you're off-grid, you want to do DC coupling. And the reason is this: if the grid goes down, your batteryless inverter turns off, and then you're running off your battery bank. Well, then your battery banks run out of juice, and then you're out of power. And so, in this circumstance, your solar array has not turned back on, again, because it's tied into the grid. That can be kind of infuriating. You say, well, can't the battery inverter turn the solar array back on? And the answer is, well, it can, but A, the manufacturer may not support it. Like in the SolarEdge's case, they say, we're not rating our system for off-grid. If you're doing any kind of backup power because of the grid failure, it needs to be on a dedicated critical load panel, and that's it. We're not going to allow you to supply your whole house breaker panel. And while you could do that little cheat that we looked at yesterday, or earlier in the program, where you're tying into the top of the bus bar, that voids your warranty, and that's not something the manufacturer is even going to tell you that you can do. Whereas with DC coupling, what happens if your batteries run out of juice, when the sun comes back up, they'll turn on your solar array, which will turn on your charge controller, which will charge your batteries back up. So in a DC coupled system, if your whole system runs out of power, the sun comes up the next day and recharges it back as soon as it can, and that'll wake up your battery inverter and start powering the load again. Whereas in a AC coupled system, if your batteries run out of juice, even if you do a configuration where you're powering your main breaker if your batteries run out of juice, all of a sudden you don't have the power necessary to turn the solar inverter back on so that the modules can start recharging the batteries. And so in an AC coupled system, the danger is your battery power could run out, and then it would be difficult to get your solar array to recharge those batteries. Whereas with a DC coupled system, it happens easily because the solar array is on the battery side. It doesn't have to go through multiple inverter systems to get to the batteries. Although the counter argument is that is even kind of bogus because if you are living off grid with an AC coupled system, what's very likely is that also tied into this is you're going to have a generator. And so if your batteries run out of juice, your generator is going to click on and keep them charged back up. And so that last argument I just said about this, the sun coming up and turning the solar array, being able to turn on the charge controller and charge your batteries, which would then turn on your battery inverter and power your load, versus not being able to turn on the solar array because the battery inverter is dead. That issue is completely resolved no matter if you're DC or AC coupled because you have a generator. And so I would say the industry really needs to stop talking about whether or not DC coupling or AC coupling is better, because the price difference between the inverter and the charge controller are very close together. If you're AC coupled, if you're connected to the grid, you're probably going to do AC coupling just because you're retrofitting a batteryless system with batteries, and that's going to be the cheapest way to do it. There is a little bit, a slight cost advantage, a slight efficiency advantage that as the off-grid market heats up, that advantage should become more clear. But right now the off-grid residential market is still in its infancy. And so AC coupling versus DC coupling is very close together. And all the disadvantages of doing AC coupling instead of DC coupling are pretty much resolved by that backup generator just turning on for 15 minutes and waking up the system and getting the solar array back up to where it should be, or turning on before then and making sure the batteries don't run out of juice, or programming the battery inverter so that it cuts off before it runs out of juice so that I can wait until 9 a.m. the next day to turn back on again so it has enough reserve power to start up the solar inverter so that the sun can get through. So I guess what I'm trying to say is let's just leave the discussion of AC coupling versus DC coupling aside, because the pros and cons are too close together to really merit more time in this program. So let's talk about charge controllers. It used to be, back before I got into the solar industry 10 years ago, 20 years ago, every solar array had a charge controller because every solar array was powering some sort of off-grid application. But charge controllers have been eliminated from system architecture with the advent of grid-tied batteryless solar. So you might have been in the solar industry for 10 years and never installed a charge controller before. So here's a couple of popular charge controllers, and they come in different shapes and sizes. My favorite charge controller, it's going to hurt people to say this because in the solar industry, Outback has a reputation for just being what USA solar installers really stand behind and love. Midnight, for that matter, has a superior reputation. In fact, SMA a very high quality inverter manufacturer. They didn't have a charge controller in the US in their product line, and they said, well, Midnight, you do such a good job making charge controllers, and we have a rock solid quality reputation, so Midnight, you're just going to make our charge controllers for us in the US. And you can kind of see the aesthetic similarities of where Outback has come and kind of made their charge controller look very similar to Midnight's. Morningstar has been on the market a long time. You know, they have a good reputation as well. I don't have any direct experience with them. Victron is a popular Australian inverter. I'm looking at Victron as an alternate to that lower cost Ames inverter that we were looking at earlier. And so in addition to buying the inverter, they also sell charge controllers to look at. You know, Magnum, just like Outback, is a battery inverter company, and they have their own brand of charge controllers. You know, my preference, my favorite charge controller is Schneider. And that'll elicit groans because Schneider's like the king of the mountain. You know, they're the big box store of solar components. They own Square D, you know, electrical service panel manufacturer. You know, Schneider is a big name in just every kind of electrical part. But, you know, Schneider and Morningstar too, they're the only two charge controller manufacturers who make a 600 volt charge controller. Well, what do you mean? You know, if you're a solar installer, especially in the residential world, you're used to designing around 600 volt circuits. So does that mean if I don't have a 600 volt charge controller, does that mean my solar circuit that plugs into the charge controller can no longer be 600 volts? Yes, that's exactly what that means. A lot of these other charge controllers, it's very common for them only to be 150 volts. Whoa. I'm used to doing on a 600 volt circuit maybe 10 modules, sometimes 9, sometimes 11. And it depends on the job site. Well, if I go from a 600 volt charge controller down to 150 volts, does that mean my solar circuit going into a charge controller is only going to be, you know, 10 divided by 4, you know, 11 divided by 4? Does that mean my 150 volt charge controller is only going to have 2 or 3 solar panels on it per circuit? Yeah, I'm used to doing solar arrays that are 30, if not 50 solar panels for off-grid. You know, 2 pallets of modules is where I would start. You know, 50 solar panels is where I would start. And I feel much more comfortable when it's 3 panels. You know, 75 solar panels. And so if I put them on a whole bunch of 3 module circuits, that means I'm going to have, you know, 75 divided by 3. You know, I'm going to have dozens of circuits to wire. Whereas I'm used to doing solar where it's only 2 or 3 circuits, and for a particularly large array it might be 5 or 6 circuits, and now I'm looking at dozens. Well, that sounds horrible, especially if the solar array is on the rooftop. Why are all these charge controllers 150 volts? Well, the charge controllers came around before module level panel electronics. And so if you're living off grid, you're particularly concerned about shade. And one way to mitigate shade is to have smaller circuits and wire them in parallel to each other. And so charge controllers came out to be from an area when the modules were more expensive. maybe you're camping in the woods, you got a lot of tall trees around, you got a lot of shade around. You say, okay, well, we're going to end up doing smaller circuits. And for a ground mount, where the wires are all accessible for any kind of maintenance and repair, dealing with dozens of circuits is, it's not fun for install, but it's not the end of the world. You do a combiner box if you need to, combine your charge controllers before landing on your inverter. Well, and so the point of it is a lot of these charge controllers, I think Outback has now gone up to 300 volts instead of 150. But if you're looking for a true 600 volt charge controller to limit your circuit number to improve the efficiency of your install, you're really going to choose between Morningstar and Schneider. And I like Schneider. It's kind of a coin flip. I don't really have enough technical knowledge to speak to Morningstar, although they were highly recommended alongside Schneider by the distributors that I looked at. And I said, if you're a solar installer, you probably don't have a lot of experience installing charge controllers, and that's not true, actually. Your SolarEdge DC Optimizer is a charge controller. And I was just complaining about, circuits that were only 150 volts, and so you have 2 modules a circuit or 3 modules a circuit. Well, your SolarEdge DC Optimizer is 1 module a circuit, and it is a voltage regulator that regulates the voltage coming out of your solar array. And that, in fact, is what a charge controller does. It regulates the voltage. So in National Electric Code, the term charge controller becomes the term voltage regulator. So charge controllers aren't that big of a deal. In fact, if you just have 1 solar panel and maybe you're a hobbyist or a tinkerer, you can buy charge controllers on Amazon for $15 or less that you can plug 1 solar panel into and 1 12-volt battery into, and all of a sudden you have an off-grid DC system that will power a USB port or a 12-volt device of some sort. The downside of getting into these high voltage charge controllers, these more powerful charge controllers, these residential off-grid charge controllers, is the amperage output for a whole house, it starts to escalate. So the amperage output for 1 charge controller for Schneider that can handle 4.8 kilowatts of power, at 600 volts, 4,800 divided by 600, that's an 80 amp charge controller. You upsize your breaker by 25%, that's a 100 amp DC breaker. And can you name another 100 amp DC device? I couldn't. Maybe a DC water pump. How many people do I know have a DC water pump in their house? Not, I could say maybe farmers do, but that'd just be a complete guess. I mean, it's not like I know that Old MacDonald has a DC water pump personally. Maybe a swimming pool pump. I don't know how high amperage those get. Might not be 100 amps. And so you go to Schneider and you say, okay, I'm buying your $1,000 charge controller. And then they say, oh, well, you need a 100 amp breaker. You say, okay, well, give me a 100 amp DC breaker. I say, okay, that'll be $1 an amp. They'll sell you the amp for each 100 amp breaker for $100 each. And so that adds 10% to the cost of the charge controller. And if you're doing, 3 pallets of modules, you're going to be buying either 3 or 4 charge controllers. And, I like to count pennies. We're counting $100 bills when it comes to these DC breakers. And so, when I made this design mistake and I shot from the hip, and we had 3 charge controllers, and I ordered 3 80 amp breakers, and they really needed to be 3 100 amp breakers. As soon as those breakers started to trip and I realized, hey, we are getting up to our maximum rated capacity, I do need to swap out these breakers for the system to function as sold. I had that sinking feeling in my stomach where it's like, oh, I made this mistake. This is clearly a design mistake. I need to go buy 3 $100 breakers and swap them out with the 3 $80 breakers. And then I'm not going to have any use for those 3 $80 breakers either. What a costly design error. Well, so what I did is I went and I looked at the breaker installed, and it's not a Schneider breaker. It was a different manufacturer listed right on the side of the breaker, and I plugged that into eBay, and I actually found a bank of 3 breakers that were 100 amps, single pole breakers. It kind of looks like a triple pole breaker, and I was a little nervous when I bought it, because I didn't know if it was really a 3-phase, 3-pole breaker, or if it was what it appeared to be, which was 3 single-pole breakers kind of ganged together. And it turned out that they were what they appeared to be. They were 3 single-pole, or what they were listed to be, which is 3 single-pole breakers. And so I found this on eBay where the whole set of 3, and actually the one I bought was a set of 6. It only cost me $50 instead of $100 each. So the whole thing cost me $50, and I ended up with 3 extra DC breakers on top of that, instead of buying 3 breakers for $100 each. So why was there such a huge difference in price? Well, it's all that these breakers are very few and far between. And so the breakers that I was buying probably came out of some medical equipment or some well pump, and that got taken apart and disassembled, and no one else has any use for these giant 100 amp DC breakers, so they sell on eBay very cheaply. But if you go and buy that specific single pole breaker, that's what everyone's looking for, and they charge accordingly for it. So what I learned from that lesson was that DC breakers, you want to buy kind of ahead of the rest of the project. As soon as you know the breaker sizes, start pricing them out, because you can find some really good deals on them. And that's the one item that might not be worth buying with the rest of the system. You can go out and a couple hours of online research will save you a couple $100, and at that point you can not fear the balance of system costs associated with DC applications. Then that's the big advantage there, is if now I know that if I wanted to put 4 charge controllers or 5 charge controllers on the same DC service panel, that I wouldn't be looking at $500 of just breaker costs, although that's what it might appear like at first glance. Let's keep going into control room layout and kind of round out the rest of what's supposed to be the first 3 hours of the program. Now we're kind of over time on that, so I'm probably gonna have to go in and adjust some of these. Well, actually, no, let's take a break. I'm going to upload this video to YouTube and get back into control room in a little bit. So, check out the YouTube channel. It has the previous videos so far. We're just making way through our residential masterclass. We're going to talk about National Electric Code and how it relates to the battery room layout next, and then continue on with our discussion from there.